So the next speaker we have is someone I am just very excited to introduce and to have here at the conference. I read an article that he wrote in the Scientific American about 5 years ago, and I was so impressed with it, I saved that issue of the magazine. I save a lot of them, through the years, but that one I thought, this is something I want to refer to again and again. And then when the prospect came to have him speak here, I was really excited, and he was so gracious, just no problem, I'll be there. And I thought, wow, this is great. Mark Jacobson is the director of the Atmosphere Energy Program and professor of Civil and Environmental Engineering at Stanford University. He's also a senior fellow of the Woods Institute for the Environment and of the Precourt Institute for Energy. Mark develops and applies computer models to understand air pollution, global warming, and renewable energy sources. In his TED Talk and appearance on the Dave Letterman Show, he explained how the world could completely convert to clean energy by 2050. He has published 2 textbooks and 140 peer-reviewed articles. Mark has received awards from the American Meteorological Society, the American Geophysical Union Ascent Award, and the 2013 Global Green Policy Design Award for developing state and country energy plans. He also served on the advisory committee to the U.S. Secretary of Energy. He has degrees in civil engineering, economics, and an MS in environmental engineering from Stanford University, and a PhD in atmospheric sciences from UCLA. And we're going to see some of the models he's been working on. Please welcome Mark Jacobson.
Great to be here. And what I want to do today is talk about these energy plans that we've been developing to change the infrastructure of states and countries of the world, or states of the US and countries of the world. And really, but I want to start by kind of motivating the plans. Why do we want to make such a change? And so maybe I don't have to convince this audience, but there is a lot of interesting information and useful information that most people are not aware of, so I'll try and go through that a little bit as well. So the first step in this is really, well, why is this problem important? From our point of view, we look at it from an air pollution, a climate, and energy security point of view. So air pollution causes 3 to 7 million premature deaths worldwide each year, most of them in developing countries. But in the United States, it's about 60 to 65,000 per year, including about 13,000 per year in California. And this is equivalent in terms of cost to about 3.3% of the GDP of the US and also worldwide similarly. Global warming is a significant issue and growing. The Arctic sea ice is disappearing rapidly and may melt entirely within 10 to 30 years. And because ice is reflective, if you get rid of the ice, you have a dark ocean below that absorbs more sunlight and heats up even faster, melting the ice faster in a positive feedback. So this is a potentially dangerous tipping point if we melt all the Arctic sea ice. And the other issues are simply that, energy costs are going up and populations are increasing as energy demand is increasing. And fossil fuels, the reason energy prices go up so fast is fossil fuels are a limited resource. You have to mine and refine and transport them. And so all these costs go up over time. Whereas if you go to renewable energy sources, the fuel cost is zero, the electric power sources. So you can stabilize energy prices, as we'll see. But energy price stability is a major issue. And also jobs are important issues. And as we'll see, you can get a huge number of job increases with converting to renewable energy and changing the energy infrastructure. Well, these are all important problems. Just to give us some examples of air pollution, this is Beijing, China, and it's equivalent to smoking about 2 packs of cigarettes per day. And in China, about 1 million people die every year prematurely from air pollution. So this is one of the things I mentioned was a significant problem. In Los Angeles in the 1970s, it was also equivalent to smoking 2 packs of cigarettes a day. And these are the lungs of a teenage non-smoker who died in Los Angeles in a car crash. And you can see their lungs are all black because of the air pollution. And this is what most of the cities of the world, the air pollution results in. Even in the US, the average person living in a city loses about 6 months of their life due to pollution. And in terms of climate, as I mentioned, well, the world is heating up rapidly. Since this is from early 1900s, since the early 1900s, about 0.9 degrees Celsius, which is on the order of 1.6 degrees Fahrenheit warming. And most of this is in the northern latitudes. You can see where the red is. This map shows the change in temperatures between recent years and the early 1900s based on measurements. And you can see that there's this huge warming at high latitudes in particular, partly due to this positive feedback that occurs, and there are other feedbacks that occur as well. But the warming is prevalent worldwide on average, although you'll find local cooling in some places that's temporarily, but on average you'll find warming in most places of the world, and there's a global average warming of 1.6 degrees Fahrenheit since the early 1900s. Now you might ask, well, what causes this warming? Well, the net global warming is on that right bar, and that's, at that was written at about 0.8 degrees, so it's 0.8 to 0.9 degrees now. But that's due to greenhouse gas warming, which the major greenhouse gases the major greenhouse gas is CO2, which causes about 40% of all warming. Then there's methane and nitrous oxide and ozone and chlorofluorocarbons contribute to warming. So that's the left bar. So if you just look at greenhouse gases, they would cause a lot more warming than is observed on the Earth. And why is that? Well, we'll see pretty soon. But another component of warming that has been overlooked until the last few years is soot from fossil fuels, biofuels, and also now biomass burning, and which is mostly black and brown carbon. A lot of it comes from diesel exhaust and kerosene burning and jet fuel burning. And in biomass burning, dark particles in the sky that affect they not only absorb sunlight, unlike greenhouse gases which absorb heat radiation from the Earth, particles that are absorb sunlight heat up over 1 million times more per unit mass than carbon dioxide, but there's a lot less of it, and it comes out of the atmosphere a lot faster. So you can imagine if you can control black carbon as a source of emissions, you can actually slow down global warming rapidly, although you'll never, because it's not so important as CO2, you still need to control the CO2 to actually stop global warming. But the fossil fuel and soot, and biofuel soot, it's the second leading cause of global warming after CO2 and ahead of methane. But as I mentioned, it has a short lifetime in the atmosphere, so if you can stop its emissions, it'll come out fast. It's actually, when it deposits on snow, it also darkens the snow, increasing the albedo or decreasing the albedo or reflectivity, therefore causing the snow to heat up faster and melt faster. It does the same thing to clouds. Over China, there are very few clouds anymore, not over China, but over Beijing and other big cities that have lots of pollution because the soot particles tend to burn off the clouds really rapidly and cause more of a haze than cloudiness. And this actually increases the amount of sunlight that reaches the surface by decreasing the reflectivity of clouds. So the soot causes 3 major impacts on clouds, on the air, and on snow and sea ice. But then there's a small amount of urban heat island, and you add those up and they cause way more warming than is observed. So what's cooling is there are other pollution particles that are reflective and enhance cloudiness, and these cause cooling. And so those are like sulfate and nitrate particles and certain organic material and ammonia. And they actually mask or offset about half of global warming. And so if you actually just cleaned up all these cooling particles, you'd suddenly double the temperature warming of the Earth, which is pretty scary because we want to clean those particles up and the black carbon because they all are the components that cause 90% of the air pollution deaths. So we want to clean up all the pollution particles, but if we do that, we're going to warm the Earth even faster. So what do? You really have to eliminate all the emissions of both the gases and the particles. And if you do that, that's the only way you're going to actually solve these problems simultaneously. And so this is what I want to talk about how to do, how to change the energy infrastructure to eliminate emissions, all emissions from combustion. So since this is what is really the problem, it's combustion, and it doesn't matter what is being burned, anything that's being burned is contributing to this problem. So we've looked at, a few years ago, we evaluated different energy sources for solving these problems in the different sectors. The major sectors are electricity, transportation, heating and cooling, and industry. And we then ranked these different energy technologies for each of these sectors and came up, after doing an evaluation looking at the impacts of these different technologies, we came up with what we thought were the best technologies, and then I'll explain why some of the other ones are not listed. But in terms of electric power, wind, solar photovoltaics, concentrated solar power, geothermal power, tidal wave power, and to the extent that it already exists, hydroelectricity, although a lot of people do not want it to grow at all, and we can phase it out eventually, but it actually has significant advantages, the existing power, in terms of load balancing and the fact that there's actually no combustion emissions associated with it, except for during the building of the dams. But that's obviously it's controversial, but it's we're talking about existing, so all our plans for the US, for example, there's no growth at all of hydro, we just use existing power, except make existing dams more efficient. Now in terms of transportation, we'd use battery electric vehicles powered by these same electric power sources, or some hydrogen fuel cell vehicles, or some hybrid. And for aircraft, you'd use cryogenic hydrogen, which would result in larger airplanes but less massive. And so it's about the same total drag and the same total cost of energy. In terms of heating and cooling, you'd use heat pumps these are all existing technologies, heat pumps which run on electricity and can be run in reverse for air conditioning. And these are ground source or air source or water source heat pumps. They extract heat out of the ground, air, or water, and they, as I said, run on electricity. And some electric resistance heating. For industry, we'd also use electric resistance or some hydrogen for heating, high temperature processes. So I'll go into more details how this would lay out. Now, what we do not recommend is nuclear power, coal with carbon capture and sequestration, or natural gas or biomass for electricity. And for vehicles, no liquid biofuels, so no corn or cellulosic ethanol or soy or algae biodiesel or compressed natural gas. And it's not because some of these are not better than what we have today. In some cases they are, some cases they're worse. But it's because they're not nearly so good as the other options that I just mentioned in terms of reducing air pollution, reducing climate relevant emissions, and stabilizing energy prices. So let me give you some examples. Well, why not natural gas? Well, first, natural gas, it emits on the order of 60 times more air pollution and carbon dioxide equivalent emissions compared with wind power per unit energy generated. And so it's an opportunity cost if you just want to emit more than use natural gas. There's also a lot of black carbon from natural gas flaring and the mining process. About 5,000 of the 63,000 or so deaths per year in the US due to air pollution are due to natural gas emissions associated with the mining and transport and use of natural gas. And gas wells, there are hundreds of thousands of gas wells spotted over the whole US, and they cause lots of land degradation. And hydrofracking is an invasive method of extracting natural gas from underground in rocks by cracking the rocks. So you inject chemicals laced with water laced with chemicals under high pressure, and that results in higher methane leakage. That is an issue, but it also requires more energy, and so there are a lot of problems associated with that. But anyway, in terms of land, in terms of emissions, it's not a good option compared with the wind, water, solar. Why not what's called clean coal, or coal with carbon capture and sequestration? That's where you would take the CO2 from the exhaust stream of a coal-fired power plant and pump it underground. Well, that takes a lot of energy. In fact, it takes 25% more energy than you would need just to run the coal plant. So that means, and you don't reduce any of the emissions from the upstream mining and transport of the coal, which is on the order of 40% of the emissions. So you actually increase coal use by 25%, and you don't actually reduce any of the other pollutants aside from CO2. So you actually increase those all by 25%. So it's actually dirtier than regular coal because of the higher air pollution. The only thing that gets reduced is CO2, but still, even with those reductions, you still have on the order of 50 times more CO2 per kilowatt hour generated than wind power. So it should really be called dirty coal. Now, what about nuclear power? Well, nuclear, you think, oh, there are no emissions associated with it, but that's not true, because you have to mine and refine uranium continuously throughout the lifetime of a nuclear power plant, and that's very energy intensive, and also the construction of the plants as well. And there's the fact that it takes so long to put up a nuclear power plant, between 10 and 19 years on average in the US for permitting and then constructing the plant. While you're waiting around for that, you could put up a solar or wind farm in 2 to 5 years. So the difference in that time frame is the opportunity cost emissions associated with running the regular electric power grid. And that's about half the emissions. So you end up getting about a total of 9 to 25 times more CO2 equivalent emissions from nuclear compared with wind power. And that doesn't even account for the fact that 1.5% of all nuclear reactors ever built to date have melted down to some degree. And 5 countries have developed nuclear weapons capabilities secretly under the guise of civilian nuclear energy programs. So if you expand nuclear worldwide in a large-scale energy conversion project, you're going to get more countries converting into nuclear weapons and more risk of meltdowns. And also there's unresolved waste issues. What about, well, biofuels? Well, if you burn liquid biofuels, you cause about the same or sometimes greater air pollution compared with gasoline. And so whereas if you go to electric vehicles, you can reduce, and you use like wind energy, for example, you can reduce 99.8% of all the emissions. So in terms of air pollution, there's no comparison. In terms of climate relevant emissions, depends on whose study you believe. But if you use corn ethanol, it's about the same emissions as gasoline, especially if you account for land use change, then it even becomes more emissions. If you use cellulosic ethanol, this has been talked about since 1981, and there's still not a single commercial cellulosic ethanol factory in the US or anywhere, then you could at best reduce 50% emissions of CO2, but not of the air pollutants. That actually goes up more than gasoline. But if you count for land use change, then you can actually, again, have more emissions of CO2 than gasoline. But that's not even the issue. This will never happen just because this is how much area it would take of the US to run the US vehicle fleet on cellulosic ethanol. And so that's whereas this is corn ethanol, so this is on the order of 15% of the entire US, including Alaska.
What is cellulosic?
Oh, it's from like switchgrass. It's cellulose in certain types of plants. So, yeah, it's and then nuclear power, to power the whole US, this is the area required to power the whole US vehicle fleet. Nuclear power would not take up a huge amount of area, about the size of Rhode Island, so we can sacrifice Rhode Island for this. Now, wind takes up about 0.5% of the US for the spacing in between wind turbines, but only 1 to 3 square kilometers of land on the ground for the turbine bases. But you can use all that space in between for rangeland or farmland or pasture land, or some of it, or it could be offshore, which you don't use any land. So it's, in terms of land area, wind to power the US vehicle fleet is 1/30th the land area for the spacing compared to corn ethanol, and 1/1,000,000th of the land area in terms of footprint. Now, solar and geothermal both have less spacing area than wind to do the same thing, but more footprint. So, but the ones we're looking at here are wind, solar, and geothermal, and they're all, the relative land area to power the vehicle fleet is not a huge amount. I'll show you a map pretty soon about how much land area it requires to power the entire US for all purposes in 2050, and so I'll get there in a second. Now, this chart gives the terawatts of total power worldwide in 2010 as about 12.8. So the world power demand in 2010 was 12.8 terawatts. That's end-use power demand. That's trillion watts of power. And if we go to 2050 with conventional fuels, that go up to almost 22. But if you converted everything to wind, what we call wind, water, and solar, so because everything would be electrified, and even the hydrogen is produced from electricity, you actually get a huge power demand of 30% reduction just by converting to electricity, because electricity is so much more efficient than burning. So for example, in an electric car, the plug-to-wheel efficiency is 80 to 86%. In other words, 80 to 86% of the electricity that goes in the car goes to move the car, and the rest is waste heat. In a gasoline or diesel car, about 17 to 20% of the energy in gasoline actually goes to move the car, and about 80 to 83% is waste heat. So you reduce your energy demand by a factor of 4 to 5 by going to an electric car. As a result, the cost of electricity for driving an electric car is 1/4 to 1/5 of that of gasoline. So it costs about 80 cents a gallon equivalent to drive an electric car versus $4 a gallon for a gasoline car. So if you drive an electric car for 20 years at 15 years at 15,000 miles per year, which is the US average, you'll save $20,000 in fuel costs. And if the price of gasoline and electricity both double, you'll save $40,000. So it is clear that an electric car is much cheaper on average, even if it would cost $5,000 to $10,000 more up front than a gasoline car, because of the fuel cost is so small, so low. Now you can see a lot of this reduction in power demand is due to that efficiency of electricity. And only 5 percentage points of that reduction here is due to end-use energy efficiency improvements, like better light bulbs or changing your habits. Whereas you could actually get a lot more, but we're being very conservative in these numbers. So when you get to the US, you can get up to a 38% reduction of power demand just by converting to wind, water, and solar. And in California, it's about 44% reduction because so many people drive cars, and that's where you get most of your benefit. So there's this huge reduction. So then we want to actually power the 2050 numbers worldwide and in the US and California, each state, with wind, water, solar. So this is one way to do it. So this is for the entire US. It gives you one scenario of how to power in 2050 the entire US with wind, water, and solar for all purposes. Now, these numbers at the top is onshore wind, and this, we actually did this state by state, and this shows the cumulative numbers over all the states. But so US-wide, it would be 31% wind, 31% onshore wind, 19% offshore wind, so a total of 50% wind power. Almost 5% residential rooftop solar, 4% commercial government rooftop solar, 30% PV power plants, 7.5% concentrated solar power plants, 1.3% geothermal, 2.5% hydroelectric, and then 0.5% tidal plus wave. And that on the right gives you the number of devices you would need of a given size. And this is the map showing how much land and water area this would all take up. And so in the case wind takes the largest amount of land area, but that's for the spacing. So actually it's mostly open space that you can use for agricultural land, range land, grazing land, farmland, or open space. And the other areas, the actual footprint on the ground, well, all the solar, the rooftop solar doesn't take up any new land. It's just the concentrated solar and the utility scale solar take up most of the new land. But it's less than 1% of the US in terms of footprint on the ground would be required to power the entire US with wind, water, and solar. And this does not account for all the reductions in land required by getting rid of every refinery, getting rid of every power plant, existing power plant, all the gas pipelines, getting rid of nuclear power plants, etc. Now, well, this is not a very good graph. This could be anything. Okay, well, but what this was showing was the world solar resources, and it was showing that, well, worldwide, in 2050, we'll need about 15 terawatts of end-use power, And worldwide, there are about 340 terawatts of solar power available over land in high solar locations. So you have a lot more solar available than you need to power the entire world on its own. And the same thing with wind. Oh, good, the wind showed up. The wind, there's about 70 to 80 terawatts of wind power available over land and near shore, and you'll need about 15 terawatts worldwide. And so there's plenty of wind and solar each individually to power the entire world for all purposes. But you can't do that with other energy sources, pretty much just wind and solar. The others can help, though. One of the things we looked at was what's the impact of large arrays of offshore wind on the East Coast, for example, because that's where we'd put a lot of offshore wind. What's the impact on hurricanes? Because if you put wind turbines in the path of a hurricane, well, you might worry that the hurricane would destroy the turbines. But it turns out if you have enough, well, if you're on the East Coast, the wind speeds of the hurricane never get up to the destruction wind speed of a turbine, so you won't destroy the turbines. But you could destroy them in the Gulf Coast because you get faster wind speeds in the hurricanes. But it turns out if you put a lot of wind turbines up, we're talking about 70,000, then you can actually dissipate a hurricane. And this is shown here with these computer simulations where you extract the energy. Each of the turbines is extracting the energy of the wind and actually shutting off at its correct shut-off wind speed. But the wind speed, when you have a lot of turbines, the wind speed never gets up to the destruction wind speed, so you don't destroy the turbines if you have a lot of them. But on the left is Hurricane Katrina with no wind turbines. And the right is when you placed about 78,000 turbines to the south east of New Orleans. And you can see already that blue triangle on the top is where the turbines are, and they're extracting the energy, and this shows wind speed, and they're reducing the wind speed. So it turns out the turbines reduce wind speed by up to 50 to 60%, and they reduce the storm surge by up to 80%. So by the time the center of the hurricane got to New Orleans on the left, you destroyed a lot of New Orleans. On the right, you actually destroyed the hurricane more than you destroyed the city. So that's the alternatives, and these turbines pay for themselves over time by just normal electricity sales because they're running year-round to generate electricity. Just a couple more slides and I'll wrap it up. This is the cost of energy. People worry, well, what's the cost of these different energy technologies? Well, right now, wind is the cheapest form of electric power in the US. Great Plains wind is, that is. That's 3.7 cents a kilowatt hour unsubsidized and about 2 cents a kilowatt hour subsidized. That compares with natural gas of about 6 to 8 cents a kilowatt hour. So it's half the cost of natural gas. Solar at the utility scale is now at the same price as natural gas. It's about 6 to 7 cents a kilowatt hour at the utility scale, but not your rooftop solar, and that's still more expensive. But still, you know, even if it's competitive, even if solar and wind are competitive, if you put up half of all new installations as natural gas, then you're not going to change the energy infrastructure. You need about 99% conversion to wind and solar and everything else right away each year to actually change everything over time. Now, if you would take our 2050 mix of wind, water, solar over the US, the average cost of electricity would be about 10.5 cents a kilowatt hour, whereas conventional fuels right now are about 10 cents a kilowatt hour, but they have another 5 cents a kilowatt hour for externality cost or health and climate cost. So they're really 15 cents a kilowatt hour. So right now, wind, water, solar is cheaper, but people don't account for the externality cost usually. Society has to pay for that. Now, if you go to 2030, though, wind, water, solar is going to go down so much, it'll be about 6 cents a kilowatt hour if you just look at the current trends. And if you look at the current trends of fossil fuels, they'll go up to 15 cents a kilowatt hour plus another 5.5 cents to get to 22 cents per kilowatt hour, or up to 22 cents, or around 20 cents. So it's going to be much more expensive. That's just looking at the trends of electricity prices. And to prove that you stabilize the price of energy with wind, water, solar, if you look at the 10 states in the US with the highest fraction of electricity from wind, and they start with Iowa and South Dakota with about 30%, the cost of electricity in those states actually declined slightly in the last 5 years. All the other states went up 8%. So those states that put in wind, they actually had reduced electricity prices compared with states that didn't put up wind. And that's because, as I said, wind and solar in particular, they stabilize prices, and wind prices are so low. In terms of climate and health cost savings, in the US, about 63,000 deaths per year, and that's equivalent to about $510 billion per year, or 3.2% of the GDP. The global warming cost from US emissions alone, so it's a global cost from US emissions, is estimated to be about $730 billion by 2050. So these costs would be eliminated by converting to wind, water, solar. And in terms of jobs, we calculated using these job creation models developed by the National Renewable Energy Lab that we would create about 5 million construction jobs, 40-year construction jobs, and 2.5 million 40-year operation jobs. So it's on the order of 7.4 million total jobs, and we'd lose about 4 million jobs in the fossil and nuclear industry. So we'd have a net 40-year job gain from doing this conversion. What about reliability? The wind doesn't always blow, but the sun doesn't always shine. However, it turns out by combining wind and solar in optimal proportions that you can actually make the grid reliable. We did a study for California for 2005 and 6, and the black line on here is the power demand. This is two specific days, and the black line is power demand hour by day. And what we did was use the existing hydroelectric and geothermal, just increase solar and wind. And the wind blows at certain times, mostly at night over land in California. The solar is available at certain times. And we found that by combining, the red on the bottom is geothermal, which is base load. The light blue is wind. The yellow is solar photovoltaics. The orange is concentrated solar. And the dark blue is hydroelectric that fills in the gaps. And we found that we can match the power demand exactly hour by hour on these 2 days with wind, water, solar. But also we found 99.8% of all the hours over 2 years we could match the power demand. Only 0.2% of the hours was there not enough available. But that was without accounting for other techniques to actually match that demand, such as demand response management and oversizing the grid and using more storage, such as concentrated solar power with longer storage. And just finally, the transition timeline to get to 100% wind, water, solar by 2050 looks kind of like this. By 2020, we want all new sources of electric power, heating, cooling, transportation, and industry to be wind, water, solar, such that by 2030, we've converted 80 to 85% of the infrastructure, and by 2050, 100%. Okay, so just to summarize these plans, we developed these plans for each state of the US, and now we're developing country plans for each country of the world. And we would, if we converted the US, we would save 63,000 lives per year, about over 500 billion in costs, another $730 billion in climate costs, create 7.5 million jobs, lose about 4 million jobs. Each person by 2050 would save about $4,400 per year in energy cost savings and $3,100 per year in climate and health cost savings. And this would require about 0.44% of US land for footprint and about 2.7% for spacing. There are many ways of addressing variability, and materials are not limits, although some recycling may be needed for some materials. There are barriers such as upfront costs, transmission needs, lobbying, and politics. And but we don't think it's a technical or economic issue. It's more of a social and political issue. And just there are a lot of people in the way of transformation. Now, to that end, if you're interested in more information, the top is a website, which is pretty long, so you could just go to thesolutionsproject.org, and there's an infographic that has a map. If you page down a little bit, it's also, actually, thesolutionsproject.org is also 100.org, the number 100.org, and it goes to the same place. But you can go to a map and click on the map, and you can look at a state, and it'll tell the energy plan for that state. And actually, if you go to the bottom of the map, this website that's on the top, there's linked to it as well, so it's easier to find. And this group is really, the Solutions Project is a group of us started. It's a nonprofit that just takes these energy plans we're developing, these science-based energy plans, and tries to educate the public about them and educate policymakers and hopefully get enough people interested to start a change. And so to that end, people are welcome to check that out and see if they're interested in signing up. Anyway, thanks very much for your attention.